All right, we've looked at sequential circuit analysis. We want to move on and be able to look at sequential circuit design. Analysis starts with the logic diagram, and then it culminates or finishes with a state table or a state diagram, and then trying to figure out what the circuit does. Design of a sequential circuit is going to start with a set of specifications, and then it's going to end with a logic diagram or culminate with that logic diagram. So the other thing that we're going to be able to need to do once we get a set of specifications and come up with a state table or state diagram is we want to be able to optimize the design, so reducing the number of gates. And typically flip-flops, those are we need flip-flops for the states, for the memory elements, and they use a lot of transistors. So minimizing the number of flip-flops can often minimize the number of gates. We also want to minimize gate delay to increase frequency. So these are types of optimizations that we want to do. What we're going to look at in this video is state reduction and assignment with the intention of design optimization. So the goal is to reduce the number of flip-flops used. That would reduce the number of states in the state table. If we can reduce the number of states in the state table, then perhaps we'll be able to reduce the number of flip-flops. But in doing so, what has to remain true is the input-output requirements must remain unchanged. So reduction of the number of states doesn't always mean less flip-flops. If we have m flip-flops, then we have 2 to the m states. 1 flip-flop, we can have 2 states. 2 flip-flops, we can have 4 states. 3 flip-flops, 8 states. 4 flip-flops, 16 states. So if we wanted to, if we could reduce a state machine from 9 states to 8 states, then we reduce from 4 flip-flops to 3 flip-flops. So that seems optimal. However, if we can reduce from 6 states to 5 states, we're still going to need 3 flip-flops in order to do that, and perhaps more combinational logic sitting in front of the flip-flops. So reduction in the number of flip-flops may increase the combinational logic sitting in front of the gates, in front of the inputs to the flip-flops, and then that would in turn increase the propagation delay. But again, so state reduction is what we're going to look up here. So reducing states, and then we're going to verify that we've done that correctly using input-output equivalency. So the states, if we look at this state diagram, the states are just labeled A, B, C, D, E. We don't have binary values assigned because typically when we're doing a design, these states have some meaning appropriate to the design. This might be our reset state. This might be the state, where we're waiting for, money to be inserted. And we're just calling them A, B, C, D for now. So if it was a counter, then the value of the flip-flops would be important, and they would also be an output of our circuit. So then we'd have to consider that in our input-output equivalency. So the input-output sequences are important, and they're specified. And if there's potentially an infinite different number of input sequences that could have a unique output sequence. So we won't necessarily go through an infinite number, but we'll go through an example here. So if we, challenge of state reduction is find ways to reducing the number of states in a sequential circuit without altering the input-output relationships. So if we consider this state diagram that we just looked at, as an example, we'll just look at this input sequence starting at this initial state A. That might be our reset state. Maybe we got there from an asynchronous reset. So what we'll do is we'll go through this input sequence and we'll fill out the output sequence. Then we'll reduce the number of states and make sure we can at least verify this sample of input-output sequences. So if we start in state A here and we have an input of 0, then we're going to stay in state A and our output's going to be a 0. So our output will be a 0 while we're in that state. Let's see if I can get my pen to work. Our output will be a 0, and then our next state will still be state A. If we're in state A and our input is a 1, then our output will still be a 0, but our next state will be B. So we'll put a 0 here and then a B up here. If we're in state B and our input is a 1, then our output will be a 0 and our next state will be D. Output's a 0. Next state D. If we're in state D and our input's a 1, our output will be a 1 and our next state will be F. Oops, that's a 1 and our next state is F. If we're in state F and a 1, then our output is a 1, and we stay in state F. Then if we're in state F, we get a 0, we're going to go to G, but our output will be a 0. If we're in state G, we get a 1, we'll go to F, and our output will be a 1. We'll go back to F. If we're in state F and we have a 0, then we'll go back to G, and our output will be a 0. And then in state G and we get a 0, we're going to go to A with our output being a 0. Whoops, that's our output. Output's a 0. Then we go to state A. We're in state A. We have an input of a 1. Our output is 0. We go to state B. If we're in state B and we get a 0, our output is 0. And our next state is C. If we're in state C and we get a 0, then our output is 0, and we go back to A. So we went from A, we went up here from A to B to D, then to F. We stayed in F. We went to G, went back to F, then we went back to A. So we're trying to exercise in this test all the different, we never did make it to E, so we probably should have kept the sequence going and went from D to E and then E to F, and we never checked out this transition, and this transition. So it's not a complete input sequence in order to test all the transitions of our state machine, but it's sufficient here for our example. So what we've come up with then is our input-output sequence, and the states here are secondary importance. What's important is that this output sequence caused by this input sequence is unique. So if we reduce the state machine, we could change these states as long as we can still get the input-output sequence, and that would be our input-output equivalency. So a circuit has input-output equivalence if the output sequence produced from an identical input sequence is always the same between two circuits. So we're just testing a small sample. We don't have an always. If we want to reduce the states, we have to maintain that input-output equivalence. And it's easier to apply these state reduction procedures with a state table than with a state diagram. So we'll take our state diagram, and we'll make a state table from that. So it's already done here for us, and hopefully you should probably pause this and verify that you can get from this state diagram to this state table. So what we want to do in order to reduce the states, we want to see if for any of these states here, any of these present states, if the next state and the output is the same regardless of the input. So if we look here, let's take a look. If we look at E and we look at F, excuse me, if we look at G, E and G. So E and G, if X is equal to 0, the next state is A. If X is equal to 1, the next state is F. So they have the same next state regardless of the input, and they have the same output in that state regardless of the input. So what we can do here is we can eliminate state G. So if we eliminate state G, and everywhere we see a G, we replace that with an E. So then that becomes E, and anywhere else do we see a G? And that's the only place that we have the G. So this state we could consider a redundant state, an unnecessary state. So now we want to see if there's anything else, right? So if we look to see if anything else is the same, if we have state F here, now that F goes to E if X is equal to 0, F is X is equal to 1, the same as D, and look, is that now we have these two states being equivalent. So now what we can do is we can say, well, let's eliminate F. So if we eliminate F, and everywhere we see an F, we're going to replace that with a D. So that becomes a D, and that was the only place there was an F, right? Because we got rid of both of these two states. These two states we got rid of, and here in state E, replace that with a D. Now if we look, we see E. If X is equal to 0, the next state is A. If X is equal to 1, the next state is D. The next states are the same, but the problem here is that when x is equal to 1 in state C, our output's a 0. In state E is our output's a 1. So these two states are not equivalent. And I think everywhere else, if we don't have any of the same next states. But we've reduced this from 1, 2, 3, 4, 5, 6, 7 states to 5 states, which doesn't reduce the number of flip-flops, but it does reduce the number of states with this procedure. So again, we can remove these states. Once we remove these two states, we end up with, we now see that D and F are equivalent, so we can replace those. And we can reduce this finally down to our 5 states. So our 5 states with our state table and with our state diagram, now we want to go show that we have the same input-output equivalency. So we need to go through this again and make sure we have the same. So if we start in state A and our input is 0, our output is 0, we still go to A. In state A, our input is 1, so our output is 0. We go to state B. If our input is 1 now, our output is 0, and we go to state D. If we're in state D and our input is 1, we stay in state D and our output is 1. If a D and a 1, we stay in state D and our output's a 1 again, right? And then if we're in state D and we get a 0, our output is 0, and we go to E. If we're in E and we get a 1, our output is 1, and we go to D. If we get a 0, our output is 0. We go to E. E, we get a 0. Then our output is 0. We go to A. A, we get a 1. Our output is 0. We go to B. B, we get a 0. Our output is 0. We go to C. C, we get a 0. Our output is 0. We go to A. And we can verify that this is the same as it was in the last for the 7 state machine. So you should be able to verify that. So again, we reduce from 7 states to 5 states. We do not reduce the number of flip-flops required. The number of gates required may depend upon the state assignments. So currently we only have letters assigned for our state assignments, so we need to assign binary codes. If we're going to have, since we only have 5 states now, we're going to have 3 unused states. So those unused states, we might be able to use those to simplify, right? We can, if we're going to look at Karnaugh maps to simplify the inputs to our flip-flops, our next state equations. So that's where it might help us out to get the unused states. So again, if we didn't check all of our input-output equivalency, an implication table is something that can use to provide a systematic method for determining if states are equivalent. All right, so in the next video, we'll do the state assignment for this.